All right. The experiment I want to tell you about this morning is, in a way, the climax of this whole course we've been doing for the last 2 years. Because what you're going to see is in order to do this experiment, scientists had to understand nearly everything we've covered in this course. You know, we started out seeing the whole progression that started in ancient Greece and went through Newton. And Newton finally got to the point where he understood the basic laws of motion, how things move when they have forces on them. Then we went into electromagnetism and discovered that the basic forces of electricity and magnetism and the way charged particles behave when they interact with each other. Then we went into this long section on atoms, right? And finally, scientists proved that all matter is made up of atoms. Well, in order for the guy I'm going to tell you about this morning, his name is J.J. Thomson. He had to understand all that before he could possibly think of this experiment that he's going to do and analyze the results. And he is the guy who gets the credit for discovering what we call the electron, which is the first major discovery of pertaining to the structure of the atom. We already know that atoms exist now, and we have some evidence that we've seen in previous classes that they aren't the ultimate particles of matter, that they have some kind of internal structure. Well, J.J. Thomson is the first to start to discover that internal structure. And the experiment that he does is pretty complicated, and I'm going to try to go through it in some detail here. So if you can get this, you're all geniuses, and these last 2 years haven't been wasted. Okay. We saw the beginning of this discovery last time. Remember that the guy we talked about last time, William Crook, he had this wonderfully talented laboratory assistant that made these really strong glass tubes for him, right? He could pump all the air out of them and they wouldn't collapse and break. And he, remember, stuck a negative electrode into one end of one of these tubes that he had pumped the air out of. And he actually saw evidence of a beam of something coming out of that negative electrode and hitting the opposite end of his tube. And then he saw he could deflect it with a magnet, and what did that prove to him?
That it had to be like a beam
Yeah.
of charged particles, something like
Right.
a current in a wire,
And how were they charged?
negatively.
Yeah. So what he was seeing in his tube was a current, but there's no wire. Okay. It was just somehow these negative particles were flying down the length of his tube and hitting the opposite side of the tube. And just by seeing the way that a magnet would deflect them, he figured out they had to be negative. But that's as far as he could take it. Okay, well, the next physicist to pick up on that experiment and do something new and discover significantly more than Crook discovered is J.J. Thomson. So, and he did this in 1897. Now his basic experimental arrangement is a bit like Crook's, but a little better in certain respects, and a little more complicated. So let me start out drawing what JJ does here. Okay. We've got a glass tube. Well, let me draw it a little thicker here. Well, my artistry should be a little bit better than that. Let's try to make it a little more symmetrical. Okay. So, he, just like Crookes did, he puts his, he has a negative electrode inserted at the end of this glass tube. Okay, so this, he has a negative electrode here, and the positive is over here, and he has a slit cut in this positive plate. So what is going to happen here, just from what I've drawn so far? Dan?
You get a beam of light on the opposite side, of the hole.
Yeah, exactly. Okay, so you're going to have these negative particles flying off this negative electrode here, and some of them are going to hit this positive plate here, but we've got this little slit here, and some of them are just going to fly right through. And he has, on this end of his tube, he's got coated with a material that will light up when these particles hit it. Okay, so he gets a, he'll see a bright spot over here on the end of his tube.
Where's the positive electrode? Is it actually the one going up?
Yeah, he actually used the positive electrode here as basically his wall that he has a slit in.
And that really makes no difference, or does it make a major difference?
No. Actually, most of these negative particles that fly off this negative electrode here, they're most rapidly accelerated, okay, when they pick up speed really fast just as they leave the electrode due to the repulsion of all the other electric charges. So they get up to speed pretty fast, and then they just fly down the tube. Now, JJ has an idea here. He decides to complicate. I mean, so far what I've got on the board is basically just what Crookes did, right? But Thomson is going to go further than that. He is interested in deflecting these particles and seeing how they move if he puts a force on them out here. So he hooks up. He does this. He inserts plates here.
How does he have it like that?
How did he do it?
The other side
Yeah, he's got. Yeah, no, he's got him inserted right into his glass tube. Exactly how he did that, managed to build a glass tube around this apparatus. Again, he had a clever assistant at that. Yeah, exactly. No, it's tough to do, but somehow he did it.
Are those mirrors or just
Now, these are metal plates. Okay, now what he's gonna do is he's going to hook these things up to a battery. Let's say he arranges it so that this is the positive and this is the negative. Okay. Now
put
what?
a negative right there on
Hmm?
the other side? On the top plate, do put a negative right there.
Yeah. Well, on these plates, this one's positive, this one's negative.
Oh.
Okay.
Oh.
Okay. Now what's going to happen? Troy.
Will the negative particles be attracted to the positive plate?
Yep.
Wait, which side is positive, one side is negative on the battery? Is it the same
Oh.
as the top? What is it?
Oh yeah. Right. So it has to be this way. Now, did everybody hear what Troy just said? These negative particles are going to fly through here. Okay, they're going to enter the area between these plates. Well, as soon as they get between those plates, what's going to happen? I mean, they're negative particles. They're going to go up toward the positive plate and away from this negative plate. Okay, so they're what's going to happen to this bright spot over here? Troy. Yeah, it moves up. So you get suddenly your bright spot is up here. Now, does this tell you anything about the nature of these negative particles? Yes.
They act just like any regular negative particles.
Well, they do, but Thomson wanted to try and figure out the how negative they were, or how big they were, how heavy they were. So he's going to do some math here and see whether he can figure out some of the actual physical properties of these particles. Okay, so you've all got this basic picture in your notes, right? So let me now start into an analysis. See, the key to this is going to be how much they're deflected here. In other words, how much were they accelerated? How much were they moved when they went between these plates? Okay, so it's what goes on between these plates is what is going to give him the clues to actually figure out one key physical property of these negative particles. So that's what I want to look at now. So forget, I'm going to erase the rest of this diagram and just focus on what's happening in these plates now.
Inside that figure, is it
So is it pretty much, is it like there's no air in there?
Oh yeah, I left out that part of the apparatus, but there's I should have drawn an air pump coming out of there that there's almost no air. I mean, yeah, I mean you can't make a perfect vacuum, and actually, the little tiny bit of air that's left in there does, in a sense, serve a useful purpose because it helps knock the negative particles off that negative electrode. But there has to be less than a millionth of the normal amount of air in order for this experiment to work. Otherwise, when the negative particles try to go down the tube, they hit air molecules and they're just scattered all over the place. You can't have that. So you have to have a very, very good vacuum. Okay. Now let's look at what these things. I can understand physics, but I can never figure out how to keep these things going. These pens. There we go. Okay. So let's look at what's happening between these plates now. And let's say the length of the plates is L. And the amount that these negative particles are deflected as they go through the plate, let me call that Y. Now remember something that we covered last year. I'm going to go all the way back to Galileo here. If I take this marker and I drop it, how is that height related to the amount of time it took to drop and hit the floor? Does anybody remember? The
Square.
Yeah, exactly. The height fallen is proportional to the time squared. And what Galileo showed, just to remind you, Galileo's law of free fall H equals 1/2 the gravitational acceleration multiplied by the time squared. So, yeah.
What is that L stand for? On the plate?
Oh, this is just the length of the plate. Yeah. So, now this is, and remember the acceleration of gravity is, does anybody remember that number? Yeah.
32 feet.
Yeah, right, 30. So when something falls due to gravity, it increases its speed by 32 feet per second each second. That's what this number g is. But that's just a constant, okay, when the force is a constant. Remember. So we have actually a similar situation going on here. And it's not gravity, but the charge, the electrical charge on these plates isn't changing in Thomson's experiment. So it's a constant force between these plates. And I mean, we've got our negative particles, falling up here instead of down. But basically, they're doing this exact same thing. They are just accelerating under a constant force. So we're going to have the exact same equation that applies. So we can write y is equal to 1/2 And it's not the acceleration of gravity this time, so I'm not going to write it as g, but it's acceleration. So I'll just write it as a multiplied by the time squared. Troy.
Isn't gravity working too, so you have to like find just the force of the plate on the electricity? When you have to like do something with the gravity on the electrodes pulling them down?
Oh, good question. Troy says, well, aren't I ignoring something here? I mean, yes, the electrical force here is pushing these particles up, but gravity is pulling them down. So don't I have to take into account both forces? Yes.
But isn't the negative also pushing it up too? So there's two forces pushing it up at the same time as there's one pushing it down? Because not only is it a
Well,
change in
I mean, you can
velocity,
think of it, yeah, absolutely. You can think of it, though, as one force. What you need to know is the strength of the electric field in here, which is created by both the positive charges on this plate and the negative charges on this plate. So I'm going to take that into consideration. Okay, so you're right. You have to take into account both these positive charges and these negative charges, but I'm going to do that. It turns out, though, I can get away with ignoring gravity, which was Troy's question. And the reason is that these negative particles are flying really, really fast. And they're flying so fast that gravity doesn't have time to pull them down any significant amount. I mean, this is a very, very small fraction of a second here, and they're not really moving appreciably due to gravity. This electrical force is so much stronger than gravity that I can ignore gravity. Okay. So, well, so far this equation doesn't look that promising, right? Why doesn't it look promising? Troy. Yeah, we don't know the time. We don't seem to know anything about the acceleration. So, so far, we're not doing great. But let's see what we can do. Well, we can relate the time to a couple of other variables, at least. And it won't be immediately obvious that this does us any good, but trust me, I am going somewhere here. How is the time related? Let's say that, let's define one more variable to call v, speed of negative particles. Now, how can we get rid of that t? How can we get rid of the time? And yeah, Harry.
Well, the time is just the distance, the total distance it's traveling divided by the rate it's going.
Yeah. Okay. Exactly right. So if I want to get rid of this time, which I don't know anyway, I can write it as the distance that it travels through the plates, L, divided by the speed. I can at least measure L now. Yes?
Find the acceleration, couldn't we you try to make the plates screens to see where the light is at multiple points?
Oh.
See how fast it goes. Time.
Yeah, I mean, we're gonna get to, I mean, this y here is basically what you're going to try to use to figure out the acceleration, and that does enter into this y is the key thing that he's going to measure that is going to allow him to to make this calculation work. But we can do the same thing with the acceleration that we just did with t. Now, we still don't know v. He still has to worry about that. He's going to do something clever to figure that out. But now let's, well, first let me just write the equation now the way, replacing the time with L over V. So now we have we can write the equation that way, just getting rid of time and writing it in terms of the length of the plates and the speed of these particles. Now, what do we know about A, though? What? Yes?
Well, the
Evan.
acceleration is the change in the velocity over the change in time.
Yeah, that's true.
Or
Well, yeah, you could pursue that. It turns out that's not going to do any good. But remember what Newton's basic law was. What was his, Evan?
force equals mass times acceleration.
Yeah, let's start there. Right, this is Newton's second law, remember. Force equals mass times acceleration. In other words, if you apply, the acceleration of a particle depends on two things. Depends on the strength of the force that you're, pushing it with, and its mass. So the bigger the force, the more acceleration. The bigger the mass, the less acceleration. Now, so we can write this. Now, well, do we know anything about this force? Now, let's say that we know, remember what we've got hooked up here. I haven't drawn the whole picture here, but we have a battery hooked up to this. Yes?
Coulomb measure, I think the force of like two currents if they're parallel, how much they're attracted and
Right.
how much they're felt.
Yeah, he did. So scientists have worked out how forces are related to electric fields in here, and we know the voltage on our battery. Okay, so we know the voltage between these plates, and if you remember, the voltage is equal to the electric field between these plates multiplied by the distance between the plates. Okay, I think we covered that some time back. But it's if you know the voltage and you know the distance between your plates, you can figure out what the electric field is here. Now, what's the significance of the electric field? Well, if you take the force, remember, is equal to the charge on the object multiplied by the electric field. Now, we can regard this electric field as known because that's just simply related to the voltage, and we know the voltage on our battery. Okay, so now we don't know the charge of these particles. Okay, so that's still another. I'm not getting rid of all the unknowns here. I'm just sort of recasting the equation here and seeing what we come up with. So what does this mean? This means acceleration of one of these charged particles is the charge on the particle multiplied by the electric field divided by the mass of the particle. Okay. Well, so we're starting to get somewhere now. Let's combine all this. We're starting to get a complicated equation is what we're starting to get, right? So we have now y equals 1/2 the charge on the electric particle multiplied by the electric field divided by the mass of this particle, whatever that is. Multiplied by L squared, L being the length of these plates, divided by the velocity of these particles squared. Yeah, see. Thomson was a pretty smart guy, huh? But you haven't even seen how smart he is yet. See, he wasn't bothered by this equation. He sees that he's getting somewhere at this point. Because, remember, this y is going to be measurable, right? That's just, he can figure that out just by how much his spot on the screen moves up. L is measurable. He knows E. And look what he's got showing up in the equation now. This isn't it. I mean, he's got real properties of these particles, the charge on them and the mass of them showing up in his equation. Now let me, yeah, you're still worried about the speed, right? But we're going to get to that in a minute. That's the really clever part. Okay, so let's rearrange this a little bit and say, let me see, we got 2y v squared. All right, I'm going to have to switch colors here. Let's try green. And we're going to have an E in the bottom and an L squared, right? Is that right? Okay. So now, what has he got? He's got the charge of these particles divided by their mass. Okay, the charge to mass ratio of each one of these little tiny particles. He's got an equation for it in terms of stuff that he can measure, except for one thing. I mean, this speed. That's the only thing hanging him up at this point. But the y, he can get pretty easy. That's just directly related to how much his spot moves on the screen. The L is easy to measure. The E is directly related to the voltage, so he can get that. How is he going to get the speed? By thinking. Okay. Well, here's the thing he thinks of. See, he didn't know any more than you know. You know what Thomson knew in order to figure out this speed right now. But it's not, I'm not suggesting it's easy. But there's a force that we studied in this class that depends on velocity. That if these particles go fast, they'll have a bigger force on them than if they go slow. I mean, if you think about a wire, okay, and it have anything moving in it. It's just a piece of metal. Okay. This force doesn't work in that case. But if you set something moving in it, then this force could exert a force on that wire. Anybody? Troy? Oh, okay. It's not the one I was thinking of. Magnetism, right? Magnets exert forces on currents. What's a current? It's just moving particles. Right? If the particles aren't moving, your magnet doesn't do anything to the wire. If the particles are moving, it does. Right? Magnetism, we saw, is directly dependent on the particles moving, and it's dependent on the speed of the particles. Remember that the total force, if you have a charged particle in motion, and you have other particles around, so you have electric fields and magnetic fields, the total force that on a charged particle will be the charge on the particle multiplied by the electric field plus the charge on the particle multiplied by its velocity multiplied by the magnetic field. Remember that. Okay, this is normally when we talked about magnetism, we talked about currents, and I put things in terms of current. But if you just have a charged particle, I told you that the force on it depends on the charge, the velocity of the particle, and the magnetic field. Yes? Oh, okay. Okay, so what can Thomson do with this information? Well, if he wants to figure out the speed of these particles now, he needs to put them through a magnetic field, right, and figure out what the force is on them somehow, and that way he can figure out their speed. Now, he has a clever way of doing that. Remember the original setup where he has these particles flying through these plates. Let me make the plates a little bigger. Okay, so we had the particles going through the plates, and they're being deflected up by the electric field between these plates. Now, what Thomson thinks of doing is putting a magnetic field into this same space, okay, with coils or electromagnets, whatever, yeah, and arranging his magnets such that they exactly cancel out the force of the electric field. So with a combination of the electric field and the magnetic field, the particles aren't deflected at all. They just go straight through. Now, quiz time. What direction does this magnetic field have to be in? Actually, I haven't even figured it out yet, but let's, how are you going to figure it out? You have to stick your fingers in the direction of the current. And what direction do we want the force to be in? We want it down, okay? So the magnetic field, now here's the tricky thing. Okay, so if the current were in this direction, then I would want a magnetic field coming out of the board, right?
So yeah.
Is the current in this direction? They're negative particles, right? Okay, now we want into the board. Okay, if the magnetic field is into the board, it will push these negative particles down. Okay, so remember I used to draw fields that were into the board like this. So that's what he's going to do. He's going to arrange his coils so that he puts a magnetic field, which as I've drawn it is into the board here, that will exactly compensate this electric field. And so there's no deflection at all. The particles just fly right through those plates. Now, when there's no deflection, what does that mean? Total force equals 0. That's an interesting equation. That means that if I just think in terms of magnitudes here, or,
How'd you get that?
oh, I can do that, right? Just in terms of magnitudes. I'm not worried about signs here. Yeah. Yeah. I can put a negative in if you'd like that. Okay, so, but let's say the magnitude, the speed, not the direction, just the speed has to be equal to the electric field divided by the magnetic field. Right? Well, like I say, I mean, he knows the voltage on his battery. He can figure out the electric field from that. If he knows the current through his electromagnet, through his coils that he's using to create the magnetic field, then he knows the magnetic field. He can figure out the speed. Which was the only remaining problem in this equation.
What actually is the speed?
Oh, what is the speed? Oh, I came prepared with the charge over mass number, but not with the speed number. I'll look that up for you and tell you this afternoon. Well, I'll finish this. We're out of time right now. I'll finish this afternoon. But I'll go ahead and write the number down for you now, just so you're not in suspense all day about the charge to mass ratio of the electron. The number turns out to be 1.76 times 10 to the 11th coulombs per kilogram, which means nothing to you, except it seems like a big number. I'll tell you a little bit about what that number actually means this afternoon.
Is that the charge or the mass?
It's the charge divided by the mass. So 1 kilogram of electrons, okay, if you had a kilogram of electrons, which is a lot of electrons actually, you would have this many coulombs of charge, which is a lot of coulombs. But I'll try to put that in terms that you can actually get a grasp of physically what it means this afternoon.